let's take a look at Newton's law of cooling. So we have detectives approaching a crime scene on a breezy 60-degree Fahrenheit night in Savannah, and Dexter's already taken out his thermometer to measure the temperature of the deceased individual. The device displays 85 degrees Fahrenheit for the corpse's temperature. Dexter immediately logs the temperature with a time of 11 p.m. into his records. While police are looking for more evidence for the cause of death, Dexter actually searches for evidence in the time of death as he hopes that'll lead to a timeline for these events. So Dexter delays joining them until midnight when he takes the temperature one last time, and Dexter records the temperature at 80.6 degrees Fahrenheit. He immediately states that he knows the time of death. Is this even possible? Can this really happen? Can you determine time of death just based upon two measurements at any given point in time? Well, we actually have a formula that can help us, and it's called Newton's law of cooling. And what Newton's law of cooling states is that the cooling of an object, if you have that temperature of an object at some time, let's say little t, and we'll denote T sub O being that temperature of that object, then T sub S, that's going to denote the temperature of that object's surroundings, and T sub I is the initial temperature of the object, and R is our continuous rate of cooling. We have this nice formula that actually states the relationship between these measurements, and it's T sub O of T, little t equals T sub S, so that's temperature of surroundings, plus T sub I, which is the initial temperature of the object, minus T sub S, that's the temperature of the surroundings. That part is in parentheses, and then times E, and E being that number 2.71828, so on and so forth, raised to the RT power, where T, the little t here, is actually time. So we can apply this to this situation, and this is how we can actually get a time of death. Taking a look at the problem a little bit more, we need to organize some information. So we have a lot of information in here. We need to know what T sub O is, T sub I is, T sub S, and little t, and that whole song and dance. So the unknowns, what we're really unsure about, is the time of death and that R value, that rate of cooling. Okay. The things we do know is the T sub S, temperature of the surroundings, is 60 degrees Fahrenheit, the temperature of 85 degrees Fahrenheit at 11 p.m., and the temperature of 80.6 degrees Fahrenheit at 12 a.m. And then we know that there's an average body core temperature of around 98.6 degrees Fahrenheit, give or take a little bit. Okay? So we can use those givens to first try and find the R value, and then we'll follow that up. Once we have the R value, we can try and figure out the time of death. And this is how it works in terms of certain scenarios where we have a constant temperature and a deceased individual. So let's take a look. So Newton's law of cooling, that's our formula again. The T sub O is the temperature of the object. The T sub S is the temperature of the surroundings. The T sub I is the initial temperature. The R is the rate of cooling, and T is the time. So we're going to first work with trying to find our R value. So we have T sub S equals 60 degrees Fahrenheit. Our little t equals 1 hour, and that's because we have 11 p.m. till midnight. That time frame is 1 hour. T sub I, our initial temperature in this case, if we're doing that 1 hour time limit, we have 85 degrees Fahrenheit is when he first takes the temperature at the crime scene. And our T sub O, our temperature of object, after 1 hour has passed, is 80.6 degrees. That's the temperature at midnight. Okay, so plugging all this into our formula, what do we have? Well, we have 80.6 equals 60 plus, and then that 85 minus 80.6, and then E raised to the R power, essentially. Okay, so taking a look at all this, we have this 80.6 equals that 60 plus 85 minus 60 e to the R power. If you subtract 60 from both sides, you get 20.6 equals 25 e to the R. Now, we want to try and isolate that e raised to the R power because we're looking for that variable up in the exponent. How do we do that? We divide both sides by 25. This is just a simple exponential equation now. So 20.6 divided by 25 equals e to the R. And using that definition of logarithms, this actually gives us R equals the natural log of 20.6 divided by 25. And if you punch this into a calculator, just find that natural log button over on the left-hand side. and punch in 20.6 divided by 25, you get R is approximately negative 0.194. So we have our continuous rate of cooling, and this gives us our chance to actually find that time of death, that T. And so that's going to cause a different sort of problem. So when we go to our Newton's law of cooling in this case, we need to understand that our initial temperature is actually the temperature at the time, right when they die. So that would be 98.6 degrees Fahrenheit. That's something we're going to have to call upon. So when we plug that into our equation, that's the only thing that really changed is our initial temperature. And we have our R value now instead of our T value. So we have this 80.6, which is our temperature at midnight. We could have actually also plugged in the 85 where we have 80.6. So we had some options here. Didn't have to take this approach, we could take the other and just make sure the 80.6 is dealing with the time being midnight versus 85 would be the time being 11 p.m. So it'll change our time slightly, but we'll still be able to find an answer. So moving forward from here, what do we do? Well, the problem is pretty much the same as the previous term. So basically when we solve for R, what do? We subtract the 60 first, so you get 20.6, and now it equals 38.6, what happens inside those parentheses, and we have an e to the negative 0.194t. Moving forward from there, we divide both sides by 38.6, and so 20.6 divided by 38.6 equals e to the negative 0.194t. So we have a problem with the exponents now. We can't just say, oh, definition of logarithms, or actually we can in some regards. You could take a natural log of both sides if you wanted to, and that'll basically cancel out that e. So you have essentially that negative 0.194t equals that natural log of 20.6 divided by 38.6. And if we divide both sides by the negative 0.194, we have our value for t. And we can plug this into our calculator, and plugging it into our calculator we find that t is approximately 3.24 hours, which if you actually work with it, it's 3 hours and 14 minutes. So what do we do when we find our time of death? Well, that was midnight. So if you turn back the clock from midnight, 3 hours and 14 minutes, you actually have the time of death as 8:46. So notice it only took a couple measurements on temperature, and we can actually get a reasonable time of death real quick. And usually they're looking for within an hour or so because they can do the timeline of events. Hopefully this helps you give an understanding of the importance of exponential equations and seeing how Newton's law of cooling actually works.